Okay, thanks very much. Yeah, so unfortunately, Charles Sorensen's talk before mine was cancelled, and he would have talked about extensive form games. I was really relying on him to have done the introductions, but anyway, I'll just quickly, refresh people's memory if you haven't seen. So we're dealing with extensive form games of perfect recall. So find out extensive form games of perfect recall. Remember, this is a setting where we have imperfect information. So the game tree has non-trivial information sets. Players don't have full knowledge of the current state. So with perfect recall, basically, informally, what it says is that every player remembers its own sequence of prior actions and information sets. And apologies that I can't give formal definitions of all of these things, but it's sort of a standard notion in extensive form games. And Kuhn showed that with perfect recall, it is without loss of generality to restrict players to what are called behavior strategies, which means that they only randomize on actions at information sets independently of each other, not sort of randomizing over all possible strategies between different games. Anyway, so a normal form game is trivially encodable as an extensive form game of perfect recall without any blow up in size, but not the other way around. If you try to convert an extensive form game of perfect recall. So of course you can convert an extensive form game to normal form by just enumerating all possible strategies. But remember now, strategies are functions that map sort of information sets to actions of those information sets. And there's a heck of a lot of those functions. So if you try to sort of flatten out that game description, you would get exponential blow-up in general. If you try to do it naively, and even if you try to do it cleverly by reduced form and so forth, it's still in general exponential blow-up. Now, if this thing would work, okay, sorry, I've already flashed ahead to a couple of slides. So now, sort of, basically, what Selten noted is that in the context of extensive form games, not just Nash equilibrium, but even subgame-perfect equilibrium, by which we mean a Nash equilibrium which is also an equilibrium in every subgame, a subgame being a subtree of the game which has self-contained information sets, okay? So subgame-perfect equilibrium is also inadequate as a solution concept for extensive form games. In particular, it can still involve so-called non-credible threats, and this is sort of a standard example of where this can arise. So look at this. I mean, player 2, look at this. Player 2 would, in this, if the game came into this information set, player 2 would certainly be incentivized to go left, right? But player 2 can bluff and say, oh, if you come to either of these, I'm going to play right, right? And that incentivizes player 1 to go choose A, which gives player 2 higher payoff. But that's a bogus equilibrium, because basically, if player 1 were to move to B, player 2 would be thereafter incentivized to choose left, okay? And so to rule out this kind of notion of equilibrium, notice that this particular game has no sort of proper subgames, because there is no subtree that contains its own information sets other than the whole tree and the leaves, right? So as a consequence, you need a more refined notion of I'm having trouble. This seems to be low on battery or something. But, okay. Right. And okay. And this is in fact the game that we just saw is on this board, which is the Nobel Prize picture for Selten, getting his Nobel Prize. So in some sense, he got his Nobel Prize for, studying these refinements of equilibrium. And there's a whole zoo of these refinements. So it's not just the perfect equilibrium. So Selten himself defines both a notion of trend-in-hand extensive form perfect equilibrium and normal form perfect equilibrium, and he showed that every extensive form game has one of these at least, so the existence, right? And subsequently, there have been various other notions of equilibrium refined notions of equilibrium that have been studied. So two very well-known ones, especially sequential equilibrium is especially well-known, are Krebs and Wilson, and quasi-perfect equilibrium is another. These are all also guaranteed to exist. And so let me define these perfect equilibrium. So what is a perfect equilibrium? We'll define it through a notion of what's called epsilon-perfect equilibrium. This was first utilized by Miltersen, but there's many ways to define the same concept. So a mixed strategy profile for a normal form game and respectively a behavior profile for an extensive form game is called an epsilon-perfect equilibrium if firstly it is fully mixed. And in the extensive form context, to be fully mixed means that you put positive probability on all actions at all information sets. Okay, and and secondly, only best responses, or respectively for extensive form games, only local best responses are assigned probability strictly greater than epsilon. And by a local best response, I mean the following: that a particular player I, the actions that it places positive probability greater than epsilon on at a particular information set, something is called a local best, an action is called a local best response. It simply just changing that action changing the action at that information set, keeping everything else fixed, cannot improve its payoff. Okay, I hope that's clear. Okay, so now this defines an epsilon-perfect equilibrium, and a perfect equilibrium is just a limit point of a sequence of epsilon-perfect equilibrium where the epsilons are tending to zero. Okay, so I hope that's clear. So Chern-Lihan perfect equilibrium is defined through a limit process. Okay, not just taking some fixed point of something; it's defined through a limit process. Okay. Every extensive form game can be, of course, converted to a standard normal form. So a second notion of perfect equilibrium that's been defined and studied is so-called normal form perfect equilibrium. And this is for an extensive form game now, so I hope the terminology is not confusing. What it means is you take the extensive form game, convert it to a standard normal form, and then take the perfect equilibrium. It's a perfect equilibrium for the normal form of that game. Okay, actually, to be more precise about this, it's the perfect equilibrium induced by a behavior strategy in the extensive form. But I don't want to get bogged down in technical details of these notions. There's sort of too many different definitions flying around here. Perfect equilibrium, so this whole extensive form perfect equilibrium and normal form perfect equilibrium are actually not the same thing. And in fact, we'll see it in a couple of slides. So I don't want to spend the whole 15 minutes defining things, so I'm not going to define formally what sequential equilibrium is, but it basically consists both of a strategy profile and what are called consistent systems of belief for the players. And the notion of sequential equilibrium is also defined through a limiting process. So basically as a limit point of a sequence of so-called assessments. But I'm not going to, unfortunately, I can't define these things. So now, and then there's this notion of quasi-perfect equilibrium, which is, okay, so you can define again the notion of epsilon quasi-perfect equilibrium, which, do I want to do on this one? So there's just too many definitions. So let me just say, this notion of quasi-perfect equilibrium refines both sequential equilibrium and normal form perfect equilibrium. And let me just sort of give you, this is sort of like a Hasse diagram for, you know, the further up you are in this, the more refined you are. That means that the set of Nash equilibria is a superset of the set of normal form perfect equilibria and the set of subgame perfect equilibria, which is a superset of the sequential equilibria, except there's a little, you also need belief systems here, but ignoring that, the normal form perfect equilibrium is, you know, sort of, so basically the two most refined notions in this Hasse diagram are perfect equilibrium and quasi-perfect equilibrium. And, you know, if you try to delve into this literature of refinements of equilibrium for extensive form games, at some point it'll occur to you, my goodness, I wish there was just a most refined notion of equilibrium that just exists in every extensive form game. I actually naively at some point thought of this and it was bothering me, and at some point I asked, somebody who knew better than I did, and they said, that's impossible. And in fact, so Miltersen showed in a very simple paper, a very cute paper, that it's impossible to have a most refined notion of equilibrium for extensive form games that subsumes, let's say, perfect equilibrium and normal form perfect equilibrium, because you can have the same game where these different notions of equilibrium are disjoint from each other. Okay, in particular, in fact, this is pretty damning for Selden's notion of perfect equilibrium. Mertens gave an example that shows a game where there exists a dominant strategy equilibrium, but it is not a perfect equilibrium. Okay, so and this kind of normal form perfect equilibrium is thus disjoint from it's sort of. Let me not dwell on that more, but actually Mertens used that as an argument to say that the right notion, the quote-unquote right notion, is this notion of quasi-perfect equilibrium defined by Van Dam. Okay? Okay, so there's a whole zoo of different notions of equilibria, and you might think, oh my goodness, trying to sort of address computational complexity issues for all these things might be a headache, but in fact, we'll show that you can encompass all of this for any n-player game. You can encompass all of this by variations of the same kind of fixed point computation problem. And so, in a sense, you can give a unified treatment of all of these. So, but before I say that, let me mention that there's a surprisingly different phenomenon going on for these notions, for games with 3 or more players, for these notions of equilibrium that are defined in terms of limits, namely perfect equilibrium, sequential equilibrium, and quasi-perfect equilibrium. Something funny happens, and this was shown by Hansen, Miltersen, and Sorensen in 2010, that just checking, I give you a profile, and if I can even give you a pure profile of strategies, and checking whether it is an equilibrium, which is a trivial thing for a Nash equilibrium, is NP hard here. So if I give you, for a 3-player game, I give you a profile and I say, is this an equilibrium? It turns out that that's an NP-hard problem, right? So that might make you think, oh, maybe actually computing or approximating an equilibrium might also be NP-hard, right? After all, if checking if something is an equilibrium is NP-hard, maybe computing one is also an NP-hard problem. And it turns out that that's not the case. No, what we show is that approximating one, of course, we don't get to pick which one, but approximating one perfect equilibrium, sequential equilibrium, quasi-perfect equilibrium, you name it, anything you saw in that Hasse diagram, for any arbitrary number of players is no harder than approximating a Nash equilibrium for a 3-player normal form game. And so before I say more, let me just, I'm not sure how much I'll be able to say, but before I say more, let me just say that there's been a very rich body of work in the context of 2-player games, beginning with the very well-known work by Kohler, Megiddo, and von Stengel, going back to the 90s, where basically they exploit sort of sequence form and show you can compute a Nash equilibrium with a lambda-type algorithm, and effectively this places the problem of computing a Nash equilibrium for extensive form games of perfect recall in PPAD. Then von Stengel with Van den Elsen and Kalman showed that lambda-type algorithms also work for computing a normal form perfect equilibrium for 2-player games. Miltersen and Sorensen did the same for sequential and quasi-perfect equilibrium. So for 2-player games, it's been, I would say, pretty much beaten to death, okay? But the question is what happens for 3 or more players. So von Stengel in '96 basically gave for Nash equilibria a nonlinear programming characterization. Bernard's characterization is not quite a fixed point characterization. In particular, it doesn't by itself establish the existence of an equilibrium, the argument, but rather, so as an upper bound, it, for example, places the problem of approximating a Nash equilibrium for n-player games in P-space, okay? There's a paper actually on other topics on succinct games by Daskalakis, Fabrikant, and Papadimitriou from 2006 that kind of as a throwaway comment in the last page and the last paragraph sketched a proof that for n-player games, extensive form games, computing an epsilon Nash equilibrium is in PPAD. It turns out that their proof actually has an error, and the constructed distributions are actually ill-defined. But basically, in personal communication with Kaskalakis, he came up with a clever way to fix that argument. But basically, so this is unpublished stuff, and they're going to put it presumably in an eventual journal version of this paper. But that involves the whole machinery of graphical games and so forth that Daskalakis, Goldberg, Papadimitriou developed. And we're going to give a direct fixed point characterization for all of these and for much more refined notions of equilibrium. So, anyway, for extensive form games, nothing more was known about these more refined notions of equilibrium. So here are basically two results that I'd like to mention. I'm not sure I'll have the time to say anything about them, but so for n-player normal form games, so-called near approximation of a perfect equilibrium is fixed PA-complete. I won't be able to spend too much time dwelling on what fixed P means, but what I mean by near approximation is getting within your desired distance of an actual perfect equilibrium. Okay, so you want to get within, let's say, L infinity distance epsilon of an actual perfect equilibrium. That's fixed P complete. Now, for n-player extensive form games of perfect recall, what I show is that near approximation of all of the notions that we described, perfect, sequential, quasi-perfect, you name it, is fixed PA complete. And almost approximation, which is analogous to the notion of computing at epsilon Nash equilibrium, is PPAD complete. The problem here is, what the heck do we mean by analogous to epsilon Nash equilibrium? Because that's not at all straightforward to define in the context of these notions of equilibrium that I define by limit points. Okay? So
because the epsilon of the approximation is different from the epsilon.
Completely different. These have nothing to do with each other. So in fact, the notions of the notions that I define for this, which I kind of argue are suitable for it, they involve two parameters, epsilon and delta. So I define something called a delta-almost-epsilon-perfect equilibrium, and then I show that that's, in a certain sense, a suitable refinement of an epsilon-almost-subgame-perfect equilibrium, and so forth. So, okay, so this is the kind of fixed point function that's involved. I wish I could give just the very basic geometric intuition of what's going on here. And there's sort of a very easy take-home trick that I could describe. I'm not going to describe the stuff about it. Let me just say that an open problem is that for proper equilibrium, I don't know analogous characterizations. So this is both for normal form games and extensive form games. This is an even more refined notion of equilibrium called that was defined by Miltersen, and you can also define something called quasi-proper equilibrium. Although people in game theory don't seem to have studied this notion that much, for biometrics games, Sorensen gave a cool Lemke-type algorithm for computing a proper equilibrium via using extended formulations, sort of polynomial-sized extended formulations of the permutohedron. And but we don't know how to. I don't know how to extend this to the setting of with n players. Yeah, and if I had a minute or two, I could describe the sort of a cool the kind of geometric notion that goes into these fixed point things. How many minutes do I have? 0. Okay, so this is just a kind of not a big deal, but here's an alternative to Nash's function for computing a fixed point. We had this in our paper with Yanakakis. Suppose that I want to devise a function whose fixed points are going to give me the equilibria of, let's say, just a normal form game, and xij denotes the probability with which player I plays pure strategy j, right? Now suppose I'm going to say something completely crazy sounding. Suppose I want to make this probability, I want to make the function assign a new probability to this, which is proportional, quote unquote, proportional to this, plus the expected payoff to player I if it switches to pure strategy J and everybody else stays the same, right? This is kind of nonsense because what do I mean by proportional to this? Because this could be a negative value, right? In general, I'm not restricting the payoffs here. So what do I mean by making new probabilities proportional to these values that are possibly positive or negative? Well, here's the basic idea. If you've got a bunch of values, positive or negative, I don't care, right? And these are, the height represents the value of that particular coordinate, okay? Now I want to sort of normalize these in other words, I want to get a probability distribution out of it. Do the following thing. Take your hand, slide it down from the top, slide it down until the first point, the unique point at which the heights above here sum up to exactly 1. Okay? So now this point, let's call this point Ti. Okay? This defines a mapping from basically the profiles, the space of profiles to the space of profiles. Turns out that the fixed points of this mapping not only are the fixed points to the Nash equilibria, but this Ti value that you get at a fixed point is the expected payoff to player I at the Nash equilibrium. Okay? So
it's exactly the trick used by Kohlberg and Miltersen for the structure theorem.
Right. So this can be turned into an algebra. This is the geometric idea. It also appears in Gould-Pearce and Stacchetti. Right. Right. And this can be turned into an algebraic thing. So it turns out that this Ti, if you use sorting networks, you can compute this value using a sorting network using an algebraic formula, an algebraic circuit. Okay. And now, the thing about this gets better than, let's say, Nash's function for computing Nash equilibria is that it's incredibly flexible, and it can easily be adapted to all of these other notions of equilibrium that I was just describing. So basically, instead of adding these utilities, I can't describe to you but for example, for the case of, let's say, quasi-perfect equilibrium, I add some other stuff here, Ki, blah, 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 which is some quantity that you can compute using dynamic programming, and that dynamic program you can encode in inside an algebraic circuit. And so let me say something about just the context of perfect equilibrium. So for perfect equilibrium, remember I need each coordinate to have probability at least epsilon. So I can just slide my hand down until the sum of the top stuff on top is 1 minus n times epsilon, n being the number of coordinates, right? And that does it. That works. And the fixed points of that give me so-called epsilon perfect equilibria. And the only little thing is, okay, how do I compute this algebraically? And sorting networks do it for you. Anyway, so there's lots of bells and whistles, especially regarding the suitable notion of almost equilibrium. So the stuff that you can place in PPAD, that involves a lot of epsilons and deltas, and you can ask me if you're interested. But yeah, okay, thanks.
So this